Hello, good afternoon. My name is Sazid Noor Rabi, and I am going to talk about our paper titled Performance of Crumpled Graphene-Based Supercapacitors with Sodium Halide Aqueous Electrolytes, a Molecular Dynamics Study. Here are my co-authors. You can see the flow of presentation in the slide. I'm going to talk consecutively about each one of them. I'm going to start by the motivation behind our work, then the background and objectives. Uh, then I'm going to describe the methodology and results and discussions. Finally, I'm going to conclude and uh, explain some future recommendations. Finally, we are going to move on to the question and answer session. So the motivation behind our research, as we can see from the graphs, the production of fossil fuels and the forecast is shown here. The demand for fossil fuel is always increasing, and it's only a matter of time before we run out of fossil fuels. As a result, renewable energy has become a very popular and ever-growing source of energy all over the world. However, energy production is only one part of the equation. Another is energy storage. For energy storage, there are many devices we can see. The common devices are capacitors, lithium-ion batteries, and fuel cells. Nowadays, supercapacitors and solar panels are also being used, which are in some places replacing the conventional energy storage devices. You may ask what a supercapacitor is. It's essentially an energy storage device that bridges the gap between a battery and a capacitor. It has very high fast charging, discharging rate, and a high number of cycles in the range of millions. It can store 10 to 100 times more energy than capacitors. However, it's less than batteries. The power density is high, much higher than batteries. The charge storage is done by electrostatic absorption, whereas in case of batteries, we can see redox reactions. Here's the background behind the supercapacitor research. It all started when the Leyden jar was discovered in the early 1740s. After that, in the 1880s, the Helmholtz model was discovered, and subsequently other models were also found. In 1954, the first electrochemical capacitor patent was patented by General Electric GE. From the 1990s, supercapacitor research has seen a lot of momentum, and nowadays commercial application is becoming very common. Here we can see a simplified model of the supercapacitor with electrode, electrolyte, anti-separator. When the electrodes are charged, electrolyte ions move toward them due to electrostatic attraction. The simple model explains the double layer, which is essentially a layer formed by ion absorption at the electrode-electrolyte interface. The first layer is formed attached to the electrode, and the second layer is formed due to the Coulomb force of the charged first layer. This is called a double layer. There are three common models of double layers. The first one is called Helmholtz model, which explains the double layer as two layers of opposite polarity at the interface between electrode and electrolyte with a constant differential capacitance. The second model is the Guy-Chapman model, which explains the differential capacitance by adding a diffuse layer in which charge distribution depends on the distance from electrode. Finally, the Guy-Chapman-Stern model explains that the Helmholtz and the Guy-Chapman model, which means the Helmholtz layer and diffuse layer, could be combined to form two different layers on a single model, which explains both constant and variable differential capacitance. Now we are going to talk about graphene. It has been used as electrode material due to its high thermal conductivity and surface area. The high surface area contributes to the capacitance. In our project, we have used crumpled graphene instead of normal planar graphene, as the crumpled structure is a three-dimensional body, whereas the graphene sheet is a two-dimensional body. crumpled graphene has higher surface area. In the next slide, we can see the objectives of our study. We have uh, crumpled the graphene using lamps. We also investigated the variation of anion on the ideal thickness. We have modeled the electrolyte, which contains sodium ions and different kind of halide ions. We have studied the behavior of ions near the crumpled graphene surface by changing the surface charge and the molarity of the electrolyte and electrode. Here is the simulation methodology. The workflow is like this. First, we have crumpled the planar graphene sheet. Then we model the electrolyte. Then we combine the model to form a supercapacitor. We conducted AMD simulations on lamps. Finally, we did post-processing on MATLAB. Here we can see the crumpling of a graphene sheet. At first, we can see the crumpling starts at the edges, which is called edge bending. Then the graphene crumples with more ease, which is called self-folding. In the end, it enters the highly crumpling region, at which crumpling rate is very fast. Here we can see that we have used 25 nanometer by 25 nanometer graphene sheet. The simulation was run for thermal equilibrium. The boundary condition was SSS, which means shrink wrapped. Spherical indentation was used to create the crumpling. We can see the progression of crumpling in the photos. The electrolyte was modeled using MATLAB code. In the code, we have set the box size at first, then we have defined the variables, then we defined the molecule centers by a 3D grid. We have assigned the molecules randomly in the different positions of the grid. We have defined the molecules by bond angle and length so that we can specify the atoms. Finally, we have generated the LAMMPS data file, which contain the positions of the atoms. Here we can see the model of the electrolyte on the left, and on the right we can see the whole supercapacitor model with graphene electrodes and electrolytes. Here is the simulation domain containing anode, cathode, and electrolyte. The electrolyte is magnified on the right side photo. We can see the sodium ion as yellow, and the pink ion is the halide ion. Next, we can see the dimensions of our model. Here we can see that between the anode and cathode, there is the electrolyte, and there is a small distance between the anode and cathode and electrolyte, which is kept to avoid overlapping of atoms. For our simulation, we have used Lennard-Jones potential, which is an intermolecular pair potential, which is used for neutral atoms. It gives a very realistic result for short-range repulsion and long-range attraction forces. In long range, the forces are attractive, which are called dispersion forces. Here we can see the repulsive forces are shown as positive potential and attractive forces are shown as negative potential. Here are some simulation parameters. Pair potential, I have already said. We have used NVT ensemble and constant charge method. The constant charge method is essentially an assumption that the charge is equally distributed in each electrode atom. Here are some other simulation parameters. Now I'm going to start the results and discussions part. Here we can see the different water molecules densities. We can see the density profiles of water molecules for different types of electrolytes, which shows that ion size or electronegativity don't have an impact on the number density, as they haven't changed very much. Here we can see, we can take a better look at the density profiles of water. We can see a surge of ion density near 165 angstrom and 210 angstrom. Both are called the first water layer. In literature, the hydrophobicity of graphene is thought to be responsible for this formation due to the porous structure of graphene, We can also see some water molecules inside the electrode regions. We have compared our results with conventional planar graphene electrode and found that their peak and the peak density is 3.6 angstrom from electrode surface. In their studies, we have found that to be 4.1 angstrom, which is close to that. Here we can see the halide ions densities. Density fluctuations are seen between 0 angstroms and 150 angstrom, which is the porous portion of the graphene, crumpled graphene, indicating that negative ions have successfully entered the pore. After this portion, density values go down to the nominal density values in the bulk solution. Region up to this is known as the diffuse portion, diffuse layer. The density profiles show an oscillatory behavior with continuous exponential decay. The inner and outer Helmholtz layers are not very visible, which is due to the complex structure of crumpled graphene, indicating influencing the ions to form the oscillatory behavior. Here we can see that the fluoride ion has the highest density peak, contributing to its capacitance more than others due to its smaller size, smaller mass, and high electron affinity. Here we can see the inner Helmholtz layer and outer Helmholtz layer formed at 10 angstroms and 65 angstroms. The inner Helmholtz layer passes through the adsorbed ions, and the outer Helmholtz plane passes through the solvated ions. Studies have found that the inner Helmholtz layer should be at 5 angstroms. We have found that it's at 10 angstroms, so it's not consistent with the previous results because of the complex structure of the crumpled graphene electrodes. Here we have used this formula to find the ideal thickness of our model. We can see that sodium fluoride has the lowest thickness while sodium iodide has the highest one. In case of capacitance, however, there is the opposite effect. Sodium fluoride has the highest capacitance and sodium iodide has the lowest capacitance. We have used different charging conditions to see its effect on specific capacitance. We can see that it has a very profound effect on the specific capacitance. However, the ideal thickness doesn't change much due to the charging condition changes. We have also varied the molarity of the electrolyte, and we can see its effect here. The ideal thickness increases with molarity, and the specific capacitance also increases with molarity, which is actually not consistent with previous comparisons we have seen. This is probably due to the increased amount of cations and anions compared to the water molecules, which have remained fixed in this case. Finally, we can see the graph portraying free energy, which explains the position of highest accumulation of ions near the electrode. We can see the highest peak for sodium fluoride and the lowest peak for sodium chloride at around -4 or -5 kilojoule per mole. These results are not conclusive, however, as the simulation needs to run for more time to give a better result. We can conclude that the positive and negative ions of water, along with the water molecules, have entered the pore of the crumpled graphene. Sodium fluoride has the best capacitance among the combinations and the lowest ideal thickness. The capacitance is 4 times more compared to flat graphene electrodes. We have also seen drastic changes in capacitance due to surface charge variation, and the molarity change was not very much. However, it was significant. In the future, we want to do these things next. We want to use the constant potential method instead of the constant charge method for more realistic results. Ionic liquids and organic electrolytes have shown great potential as they have a higher potential window. TIP4P model is a better approximation of water than TIP3P model. We are also trying to use the wettability of crumpled graphene surface which might affect capacitance as well. Thank you all for attending this talk.